In electricity supply systems, an earthing system or grounding system is circuitry which connects parts of the electric circuit with the ground, thus defining the electric potential of the conductors relative to the Earth's conductive surface. The choice of earthing system can affect the safety and electromagnetic compatibility of the power supply. In particular, it affects the magnitude and distribution of short-circuit currents through the system, and the effects it creates on equipment and people in the proximity of the circuit. If a fault within an electrical device connects a live supply conductor to an exposed conductive surface, anyone touching it while electrically connected to the earth will complete a circuit back to the earth's supply conductor and receive an electric shock. Regulations for earthing system vary considerably among countries and among different parts of electric systems. Most low-voltage systems connect one supply conductor to the earth. A protective earth, known as an equipment grounding conductor in the U.S. National Electrical Code, avoids this hazard by keeping the exposed conductive surfaces of a device at earth potential. To avoid possible voltage drop, no current is allowed to flow in this conductor under normal circumstances. In the event of a fault, currents will flow that should trip or blow the fuse or circuit breaker protecting the circuit. A high-impedance line-to-ground fault insufficient to trip the overcurrent protection may still trip a residual current device if one is present. This disconnection in the event of a dangerous condition before someone receives a shock, is a fundamental tenet of modern wiring practice and in many documents is referred to as automatic disconnection of supply. The alternative is defense in depth, where multiple independent failures must occur to expose a dangerous condition. Reinforced or double insulation come into this latter category. In contrast, a functional earth connection serves a purpose other than shock protection, and may normally carry current. The most important example of a functional earth is the neutral in an electrical supply system. It is a current-carrying conductor connected to earth, often, but not always, at only one point to avoid flow of currents through the earth. The NEC calls it a grounded supply conductor to distinguish it from the equipment grounding conductor. Other examples of devices that use functional earth connections include surge suppressors and electromagnetic interference filters, certain antennas and measurement instruments. People use an earthing system mainly for these applications, to protect a structure from lightning strike, directing the lightning through the earthing system and into the ground rod rather than passing through the structure. Part of the safety system of mains electricity, preventing problems associated with floating ground and sky voltage. The most common ground plane for large monopole antenna and some other kinds of radio antenna. Other, less common applications of earthing systems include, single-wire earth return. Part of a system that powers small devices from sky voltage. One at each end of a ground dipole ELF antenna. Low-voltage systems, in low-voltage distribution networks, which distribute the electric power to the widest class of end users, the main concern for design of earthing systems is safety of consumers who use the electric appliances and their protection against electric shocks. The earthing system, in combination with protective devices such as fuses and residual current devices, must ultimately ensure that a person must not come into touch with a metallic object whose potential relative to the person's potential exceeds a safe threshold, typically set at about 50 eV. In most developed countries, 220,240 V sockets with earthed contacts were introduced either just before or soon after World War II, though with considerable national variation in popularity. In the United States and Canada, 120-volt power outlets installed before the mid-1960s generally did not include a ground pin. In the developing world, local wiring practice may not provide a connection to an earthing pin of an outlet. In the absence of a supply earth, devices needing an earth connection often use the supply neutral. Some use dedicated ground rods. Many 110V appliances have polarized plugs to maintain a distinction between live and neutral, but using the supply neutral for equipment earthing can be highly problematical. Live and neutral might be accidentally reversed in the outlet or plug, or the neutral to earth connection might fail or be improperly installed. Even normal load currents in the neutral might generate hazardous voltage drops. For these reasons, Most countries have now mandated dedicated protective earth connections that are now almost universal. If the fault path between accidentally energized objects and the supply connection has low impedance, the fault current will be so large that the circuit overcurrent protection device will open to clear the ground fault. Where the earthing system does not provide a low-impedance metallic conductor between equipment enclosures and supply return, fault currents are smaller, and will not necessarily operate the overcurrent protection device. In such case a residual current detector is installed to detect the current leaking to ground and interrupt the circuit. IEC terminology: International Standard IEC 60364 distinguishes three families of earthing arrangements, using the two-letter codes TN, TT, and IT. The first letter indicates the connection between earth and the power supply equipment, TA direct connection of a point with earth, IA no point is connected with earth, except perhaps via a high impedance. The second letter indicates the connection between earth and the electrical device being supplied, TA direct connection of a point with earth, NA direct connection to neutral at the origin of installation, which is connected to the earth, TN networks. In a TN earthing system, one of the points in the generator or transformer is connected with earth, usually the star point in a three-phase system. The body of the electrical device is connected with earth via this earth connection at the transformer. The conductor that connects the exposed metallic parts of the consumer's electrical installation is called protective earth. The conductor that connects to the star point in a three-phase system, or that carries the return current in a single-phase system, is called neutral. Three variants of TN systems are distinguished: TNAS, PE and N are separate conductors that are connected together only near the power source. This arrangement is a current standard for most residential and industrial electric systems, particularly in Europe. TNAC, a combined PEN conductor, fulfills the functions of both a PE and an N conductor. Rarely used. TNACS, part of the system, uses a combined PEN conductor, which is at some point split up into separate PE and N lines. The combined PEN conductor typically occurs between the substation and the entry point into the building, and separated in the service head. In the UK, this system is also known as protective multiple earthing, because of the practice of connecting the combined neutral and earth conductor to real earth at many locations, to reduce the risk of electric shock in the event of a broken PEN conductor, with a similar system in Australia and New Zealand being designated as multiple earth neutral. It is possible to have both TNS and TNCS supplies taken from the same transformer. For example, the sheaths on some underground cables corrode and stop providing good earth connections, and so homes where bad earths are found may be converted to TNCS. TT network: in a tearthing system, the protective earth connection for the consumer is provided by a local earth electrode, and there is another independently installed at the generator. There is no earth wire between the two. The fault impedance is higher, and unless the electrode impedance is very low indeed, a TT installation should always have an RCD as its first isolator. The big advantage of the TT earthing system is that it is clear of high and low frequency noises that come through the neutral wire from connected equipment. TT has always been preferable for special applications like telecommunications sites that benefit from the interference-free earthing. Also, TT does not have the risk of a broken neutral. In locations where power is distributed overhead and TT is used, installation earth conductors are not at risk should any overhead distribution conductor be fractured by, say, a fallen tree or branch. In pre-RCD era, the TT earthing system was unattractive for general use because of its worse capability of accepting high currents in case of a live-to-PE short circuit. But as residual current devices mitigate this disadvantage, the TT earthing system becomes attractive for premises where all AC power circuits are RCD protected. The TT earthing system is used throughout Japan, with RCD units in most industrial settings. This can impose added requirements on variable frequency drives and switched mode power supplies, which often have substantial filters passing high frequency noise to the ground conductor. IT network: in an IT network, the electrical distribution system has no connection to earth at all, or it has only a high-impedance connection. In such systems, an insulation monitoring device is used to monitor the impedance. Comparison. Other terminologies. While the national wiring regulations for buildings of many countries follow the IEC 60364 terminology, in North America, the term equipment grounding conductor refers to equipment grounds and ground wires on branch circuits, and grounding electrode conductor is used for conductors bonding an earth ground rod to a service panel. Grounded conductor is the system neutral. Australian and New Zealand standards use a modified PME earthing system called multiple earth neutral. The neutral is grounded, earthed, at each consumer service point, thereby effectively bringing the neutral potential difference to zero along the whole length of LV lines. Properties. Cost. TN networks save the cost of a low-impedance earth connection at the site of each consumer. Such a connection is required to provide protective earth in IT and TT systems. TNC networks save the cost of an additional conductor needed for separate N and PE connections. However, to mitigate the risk of broken neutrals, special cable types and lots of connections to earth are needed. TT networks require proper RCD protection. Safety. In TN, an insulation fault is very likely to lead to a high short-circuit current that will trigger an overcurrent circuit breaker or fuse and disconnect the L conductors. With TT systems, the earth fault loop impedance can be too high to do this, or too high to do it within the required time, so an RCD is usually employed. Earlier TT installations may lack this important safety feature, allowing the CPC and perhaps associated metallic parts within reach of persons to become energized for extended periods under fault conditions, which is a real danger. In TNS and TT systems, a residual current device can be used for additional protection. In the absence of any insulation fault in the consumer device, the equation IL1 plus IL2 plus IL3 plus N equals 0 holds, and an RCD can disconnect the supply as soon as this sum reaches a threshold. An insulation fault between either L or N and PE will trigger an RCD with high probability. In IT and TNC networks, residual current devices are far less likely to detect an insulation fault. In a TNC system, they would also be very vulnerable to unwanted triggering from contact between earth conductors of circuits on different RCDs or with real ground, thus making their use impracticable. Also, RCDs usually isolate the neutral core. Since it is unsafe to do this in a TNC system, RCDs on TNC should be wired to only interrupt the live conductor. In single-ended single-phase systems where the earth and neutral are combined, if there is a contact problem in the PEN conductor, then all parts of the earthing system beyond the break will rise to the potential of the L conductor. In an unbalanced multi-phase system, the potential of the earthing system will move towards that of the most loaded live conductor. Such a rise in the potential of the neutral beyond the break is known as a neutral inversion. Therefore, TNC connections must not go across plug-socket connections or flexible cables, where there is a higher probability of contact problems than with fixed wiring. There is also a risk if a cable is damaged, which can be mitigated by the use of concentric cable construction and multiple earth electrodes. Due to the risks of the lost neutral raising earthed metal work to a dangerous potential, coupled with the increased shock risk from proximity to good contact with true earth, the use of TNCS supplies is banned in the UK for caravan sites and shore suppleter boats, and strongly discouraged for use on farms and outdoor building sites, and in such cases it is recommended to make all outdoor wiring TT with a CD and a separate earth electrode. In IT systems, a single insulation fault is unlikely to cause dangerous currents to flow through a human body in contact with earth, because no low-impedance circuit exists for such a current to flow. However, a first insulation fault can effectively turn an IT system into a TN system, and then a second insulation fault can lead to dangerous body currents. Worse, in a multi-phase system, if one of the live conductors made contact with earth, it would cause the other phase cores to rise to the phase voltage relative to earth rather than the phase neutral voltage. IT systems also experience larger transient overvoltages than other systems. In TNC and TNCS systems, any connection between the combined neutral and earth core and the body of the earth could end up carrying significant current under normal conditions, and could carry even more under a broken neutral situation. Therefore, main equipotential bonding conductors must be sized with this in mind. Use of TNCS is inadvisable in situations such as petrol stations, where there is a combination of lots of buried metalwork and explosive gases. Electromagnetic compatibility. In TNS and TT systems, the consumer has a low noise connection to earth, which does not suffer from the voltage that appears on the end conductor as a result of the return currents and the impedance of that conductor. This is of particular importance with some types of telecommunication and measurement equipment. In TT systems, each consumer has its own connection to earth, and will not notice any currents that may be caused by other consumers on a shared PE line. Regulations. In the United States National Electrical Code and Canadian Electrical Code, the feed from the distribution transformer uses a combined neutral and grounding conductor, but within the structure separate neutral and protective earth conductors are used. The neutral must be connected to earth only on the supply side of the customer's disconnecting switch. In Argentina, France and Australia, the customers must provide their own ground connections. Japan is governed by PSE law, and uses TT earthing in most installations. In Australia, the multiple earth-neutral earthing system is used and is described in Section 5 of American Samoa, 3000. For an LV customer, it is a TNC system from the transformer in the street to the premises and a TNS system inside the installation, from the main switchboard downwards. Looked at as a whole, it is a TNCS system. In Denmark the High Voltage Regulation and Malaysia the Electricity Ordinance 1994 states that all consumers must use TT earthing, though in rare cases TNCS may be allowed. Rules are different when it comes to larger companies. Application examples: most modern homes in Europe have a TNCS earthing system. The combined neutral and earth occurs between the nearest transformer substation and the service cutout. After this, separate earth and neutral cores are used in all the internal wiring. Older urban and suburban homes in the UK tend to have TNS supplies, with the earth connection delivered through the lead sheath of the underground lead and paper cable. Older homes in Norway uses the IT system while newer homes use TNCS. Some older homes, especially those built before the invention of residual current circuit breakers and wired home area networks, use an in-house TNC arrangement. This is no longer recommended practice. Laboratory rooms, medical facilities, construction sites, repair workshops, mobile electrical installations, and other environments that are supplied via engine generators where there is an increased risk of insulation faults, often use an IT earthing arrangement supplied from isolation transformers. To mitigate the two fault issues with IT systems, the isolation transformers should supply only a small number of loads each and should be protected with an insulation monitoring device. In remote areas, where the cost of an additional PE conductor outweighs the cost of a local earth connection, TT networks are commonly used in some countries, especially in older properties or in rural areas, where safety might otherwise be threatened by the fracture of an overhead PE conductor by, say, a fallen tree branch. TT supplies to individual properties are also seen in mostly TNCS systems where an individual property is considered unsuitable for TNCS supply. In Australia, New Zealand and Israel the TNCS system is in use. However, the wiring rules currently state that, in addition, each customer must provide a separate connection to earth via both a water pipe bond and a dedicated earth electrode. In Australia and New Zealand this is called the Multiple Earth Neutral Link or MEN link. This MEN link is removable for installation testing purposes, but is connected during use by either a locking system or two or more screws. In the MEN system, the integrity of the neutral is paramount. In Australia, new installations must also bond the foundation concrete reinforcing under wet areas to the earth conductor, typically increasing the size of the earthing, and provides an equipotential plane in areas such as bathrooms. In older installations, it is not uncommon to find only the water pipe bond, and it is allowed to remain as such, but the additional earth electrode must be installed if any upgrade work is done. The protective earth and neutral conductors are combined until the consumer's neutral link. Beyond this point, the protective earth and neutral conductors are separate. Medium voltage systems. In medium voltage networks, which are far less accessible to the general public, the focus of earthing system design is less on safety and more on reliability of supply, reliability of protection, and impact on the equipment in presence of a short circuit. Only the magnitude of phase-to-ground short circuits, which are the most common, is significantly affected with the choice of earthing system, as the current path is mostly closed through the earth. Three-phase HV/MV power transformers, located in distribution substations, are the most common source of supply for distribution networks, and type of grounding of their neutral determines the earthing system. There are 5 types of neutral earthing: solid earth neutral, unearthed neutral, resistance earth neutral, low resistance earthing, high resistance earthing. Reactance earth neutral, using earthing transformers, solid earth neutral. In solid or directly earth neutral, transformer's star point is directly connected to the ground. In this solution, a low impedance path is provided for the ground fault current to close and, as a result, their magnitudes are comparable with three-phase fault currents. Since the neutral remains at the potential close to the ground, voltages in unaffected phases remain at levels similar to the pre-fault ones. For that reason, this system is regularly used in high-voltage transmission networks, where insulation costs are high. Unearthed neutral. In unearthed, isolated or floating neutral system, as in the IT system, there is no direct connection of the star point and the ground. As a result, ground fault currents have no path to be closed and thus have negligible magnitudes. However, in practice, the fault current will not be equal to zero. Conductors in the circuit particularly underground cables have an inherent capacitance towards the earth, which provides a path of relatively high impedance. Systems with isolated neutral may continue operation and provide uninterrupted supply even in presence of a ground fault. However, while the fault is present, the potential of other two phases relative to the ground reaches of the normal operating voltage, creating additional stress for the insulation. Insulation failures may inflict additional ground faults in the system, now with much higher currents. Presence of uninterrupted ground fault may pose a significant safety risk. If the current exceeds 4.5 an electric arc develops, which may be sustained even after the fault is cleared. For that reason, they are chiefly limited to underground and submarine networks, and industrial applications, where the reliability need is high and probability of human contact relatively low. In urban distribution networks with multiple underground feeders, the capacitive current may reach several tens of amperes, posing significant risk for the equipment. The benefit of low fault current and continued system operation thereafter is offset by inherent drawback that the fault location is hard to detect. See also: ground and neutral, electrical wiring, single wire earth return, soil resistivity. References: IEC 60364-1, Electrical Installations of Buildings Part 1, Fundamental Principles, Assessment of General Characteristics, Definitions. International Electrotechnical Commission, Geneva. Jeff Cronshaw, Earthing Your Questions Answered. IEE Wiring Matters, Autumn 2005. Merlin-Gerin Electrical Installation Guide, Chap E, Low Voltage Distribution Earthing Schemes. John Whitfield, The Electrician's Guide to the 16th Edition IEE Regulations, Section 5.2 Earthing Systems, 5th edition. E. Leonardo Energy Earthing Systems Education Center, Earthing Systems Resources.